Hi there, and welcome to Geology 101. This is your very first lecture in the class, and I think you're going to like it. Today we're going to be talking about the science of geology. Right now, before we start, I'm in a nice, comfortable situation. I'm in my daughter's room. Everybody else is in the rest of the house doing chores and what have you, whereas I get to sit here and record geology lectures. It's pretty fun, actually. Many of you are probably at a coffee house, or you've waited for the children to go to bed at night and you've got your earphones on. You're just trying to get it in as soon as you can. Congratulations. We're all kind of in this boat together, and we're all doing it in a non-traditional way, which is what this online class is all about. So with that said, let's go ahead and start talking about geology, which is why you took the class in the first place, right? So geology is the science that pursues an understanding of planet Earth. Geo, meaning Earth, and ology. A lot of people think that the word ology or logy actually means study of, but it really doesn't quite get it. The word logy is where we get the word logic from. Okay, so it's really the logic of the Earth. We subdivide the science of geology into two branches, into two subdivisions. There's one, the physical geology group, and this group here examines the materials comprising Earth and seeks to understand the many processes that operate beneath and on its surface. Whereas historical geology seeks an understanding of the origin of Earth and its development through time. The difference between these two, there's considerable overlap between them, but physical geology, which is really the focus of the course that you're in right now, is dealing with rocks, minerals, continents, oceans, what the Earth actually is, and how it interacts with one another and with human beings, as well as in the solar system. Historical geology is really a description of the historical record of the Earth and delves deeply into things such as the origins of the continents, the origins of the oceans, where the Earth came from, where did all these fossils come from? That doesn't mean we're not going to be talking about fossils in this class. We're going to see a lot of wonderful fossil images, especially towards the end when we talk about deep geologic time. But before we can get there, we need to do the more basic aspects of it and talk about things such as what continents are, what the oceans are, what the Earth is, how crystals form. And so within the first 3 or 4 weeks, you'll see that we're going to be talking about crystals and magmas and lavas and continents and how islands form, including the Hawaiian Islands where we all live today. You can see that I've got two photos here. This one here was actually taken from the University of Hawaii website right here in Hilo. So this is actually a UH student in geology over at Hilo sampling lava. You can tell this is a really great photo because you can see how hot the lava is by the fact he's shielding his face way up here, and there's no skin that's exposed anywhere on his body to the lava flow. The heat here we're talking about is many times that of the highest level setting on any furnace, or I'm sorry, of any oven that you have. So if you could set an oven to 500 and let it run for an hour and open that door, it's only about a third as hot as what he's experiencing right there. So trust me, after he grabs that sample, he's running away from that lava flow. By contrast, is the exact opposite. These two geologists here are what we call stratigraphers, and they're in the bottom of the Grand Canyon. And instead of looking at lava, where the lava is flowing out, here there's boulders, there's water that this gentleman is actually jumping across the creek on, and then, of course, the canyon walls themselves are made of these beautiful sandstone layers that go literally flat. And these guys are really doing more the role of historical geologists, and this gentleman over here is doing more the role of a physical geologist. Doesn't mean that there isn't overlap, but you get the idea. Each one of these rock layers is almost like a page right out of time that can be interpreted and read. All right. So the science of geology, we're going to keep talking about this. Geology, people, and the environment. There are many important relationships between people and the natural environment. This over here is a photograph of Salt Lake City, Utah. And here you can see, if you were in the city itself, you'd be seeing these wonderful skyscrapers, and you might be just absolutely in awe of what humanity has created. But of course, right behind it are these beautiful tectonically active mountains. To the eye of the trained geologist, these things actually generate earthquakes pretty routinely. And that Salt Lake City is actually right at the edge of what we call a feeder canyon. So a mud flow could come in and wipe it out at any time, provided the conditions were sufficient to make that happen. We pray that that doesn't happen, but nonetheless, we as human beings need to be aware of the fact that nature, as grandiose as many of our own creations are, nature's creations are sometimes absolutely fantastic and can be catastrophic catastrophic if we're not paying attention. Okay? And of course, the second bullet point here says some of the problems and issues addressed by geology involve natural hazards, resources, world population growth, and environmental issues. And of course, I had to move this here in a little break on the slide. But you can see here that this is actually a water well. It's been drilled into the ground. This gentleman here is watching it, and essentially the water is coming right out under its own pressure. There's no pump anywhere that's pushing the water out. That's just simple earth pressure pushing that water out. And why would they be so curious about the water coming out of the ground? Well, mainly because water is the most important resource on planet Earth. And fortunately for us at this time, water is relatively plentiful. But it won't always be if we don't watch our resources and watch how we treat the geologic systems that produce that water for us. There are several ways that we can approach our view of geology over time, and you'll find that I will emphasize one group over another, but then you'll see also that from time to time we have to make sure that we are aware of the fact there are multiple ways of looking at a problem. So one of the issues that we see here is that naturalists have adopted several views towards the Earth over time, and the nature of Earth has been a focus of study for centuries. That's where Aristotle comes in. Aristotle was the first one that we would call the first modern scientist. I wouldn't say that he was perfect. He didn't know really how to go about collecting data. A lot of that stuff didn't exist, such as compasses that were reliable enough for taking measurements. He would just simply go out and try to make observations and interpret them. And those interpretations lasted for a very, very, very long time. And he is in a lot of ways the father of all sciences, not just geology. The second group that came along were the catastrophists. And so catastrophism is basically a paradigm whereby we say that catastrophes are responsible for Earth's creation and features. So in other words, that the Earth was a catastrophe, that it formed from some major cosmic event, perhaps even a metaphysical event, say created through a 6,000-year creation or some other religious method. Alternatively, it doesn't even have to be that way. It could also be that the Earth formed from the fusion of two moons in space, and that's how it formed. In other words, that it happened in a very rapid succession. Uniformitarianism takes a different slant at this, right? Uniformitarianism and the birth of modern geology, and this is the paradigm under which most geologists operate under. As a matter of fact, I would say that the number of catastrophists that exist today are almost none. That exist within academia, I should say. So uniformitarianists are sometimes believe in a viewpoint called gradualism. And basically what uniformitarianism is, it has the word uniform in it. And what it's basically saying is that the rules of physics as they exist today are operating in the same manner that they have always existed, that they operated 1,000 years ago or 1 billion years ago or 5 billion years ago in exactly the same predictable way that our equations indicate that they should be working today. This is a huge assumption, but it's probably a valid assumption. There's no reason for us to believe that this isn't so. And so as a consequence, we can bring into consideration things like geologic time, how long things take to move. For example, you might look at a beach and say, it must, there's no way that you can build a beach like this in 100 years. But if you have geologic time, say you contribute to a beach a bucket of sand every year for 1 million years. Well, that's 1 million buckets of, or 1 million buckets of sand. That's a lot of sand after a while, if you take geologic time into consideration. And so we have kind of the last of what we call the catastrophists here, which is Immanuel Velikovsky, who was a Russian. And he wrote up until, I think he finally passed away in the 1970s, but he was a prolific writer in the 30s, 40s, and 50s on catastrophism. But the father of uniformitarianism is James Hutton, and he's probably the most famous single name in geology outside of Aristotle himself. James Hutton came up with the idea of uniformitarianism and was the first one to begin to make arguments that the Earth might be older than what was prevalent in England was the belief that the Earth was 6,000 years old. He made an argument that it was probably millions, even billions of years old. and actually said, unless somebody can demonstrate a beginning to the Earth, I can see no vestige of beginning, no prospect for an end. It's a famous line from him. So James Hutton, fascinating guy. He was a kind of a prickly individual. He wasn't the kindest person in the world, and a lot of people didn't like him on a personal level, but he was fairly smart. As a matter of fact, all three of these men are smart. And since then, there have been a lot of women, too. So this geology has become a much more woman-dominated research field, especially in the field of geochemistry and geophysics, actually. I've been bringing up this idea of geologic time. So geologists are now able to assign fairly accurate dates to events in Earth's history. So when we look back, we've got a pretty good idea of when things happened and how to correlate what was happening, say, in Russia with what was happening in South America. And the way that we can do that is through what we call a relative dating geologic timescale, which is to say relative dating means that dates are placed in their proper sequence or order without knowing their age in years. For example, if I was to say, I'm going to the store, or if I was to say, I went to the store, I bought myself a soda, and I bought myself a snack, and then I came home. Notice that I gave you that whole sequence. You actually understood the story very well. The only thing is that you don't know when that happened, right? But you do know the order. You know that I had to go to the store before I can get my soda and my snack before coming home. If I was to say, I came home, and then said, and then I went to the store, and then I went and got a snack, that's out of order and it's deceptive, right? So how do geologists go about looking at the Earth and doing the same thing? Well, I have this nice figure over here to kind of demonstrate in basic. We're just going to do a basic approach. We'll be doing a little more complicated ones later on in the class. But a basic approach to this is just simply say, which had to come first, right? And which had to come last? Well, obviously we have these rock layers. There's 4 rock layers over here. They're nice and flat, and they sit right across here. And they sit right across here, and we got to ask ourselves, what came first? Was it the rock layers, or was it this river canyon right here? Well, obviously, if the rock layers here had to exist prior to the river canyon, because the river canyon is cutting down through it. So you kind of get the idea of how we can put together the river canyon. Now, what about the layers underneath it? Well, here we see the Lawrencetown Formation and the Foster City Formation, so on and so forth. This one down here had to come before the one up on top, because if it wasn't there, what would be up on top? So we have the ability to put these things in sequence. And then, of course, these are all sitting on top of other layers down below. Now, notice these layers are they're not flat, they're tilted. We can actually see their layers in here, and in them there's something called a granite. We'll talk about all this stuff. That these things had to have happened in a certain order to make that picture happen. And we will, in this class, learn how to work those things out. Don't worry, they're actually kind of fun puzzles. There's nothing to be stressed out about doing them. But you get the idea that geologists are able to solve these problems just using a little bit of gray matter in their heads. Okay, so the magnitude of geologic time involves vast times, millions or billions of years, right? It also can be very short, but I want you to have a bigger appreciation for how long is. An appreciation for the magnitude of geologic time is important because many processes are gradual. Remember gradualism under uniformitarianism, right? And so here we see a dinosaur this is actually a dinosaur fossil, and it's about an 80 million year old dinosaur fossil. These are vertebrae, and you'll notice that each vertebrae is bigger than this man's hand. As a matter of fact, it's as big as his head. So you can imagine how big the spinal cord that was going through that vertebrae was, and this is just going through the tail section right here. Now, how does something like this evolve? Gradually. How does it get buried? It might have gotten buried very fast, but the preservation of that fossil over time would have been a gradual process. So as long as you have this idea that some things will happen under very short periods of time, as the catastrophists would see it, and sometimes under very long periods of time, as the uniformitarianists would see it, we'll be okay. Just quickly wanted to introduce to you the geologic time scale as we know it. So we have been able to correlate actual years to those rock layers over time by mapping out when the fossils existed and various complicated processes. Don't worry about it. We're not going to get too much into it in this class, but just know that there is a rationale for how we know all of these things. We will get a little bit into radiometric dating at the end of class. But for the most part, there's a number that you need to know, which is, for one, that the Earth is 4.6 billion years old. And this over here, this timeline right here, is supposed to, this eon is supposed to represent all of Earth history. So here's 460 or 4,600 million years, which is 4.6 billion. This is 4 billion, 2.5 billion, and then 542 million. And basically, from 542 million years ago, all the way back to the beginning of Earth history, we were in a period of time that we now classify as the Precambrian. The Precambrian is a fascinating time of Earth history, but it's not really all that interesting with respect to the kinds of animals, the plants, and the development of mushrooms and fungus and things like this. That didn't come until much later on, during a period of time called the Phanerozoic, up here. So from 542 million years ago, all the way to basically the formation of the Earth, there was life here, but it didn't have teeth, it didn't have skeletons, it didn't have vertebrae, it didn't have shells, and so as a consequence, the fossil record is very, very, very limited. It's very hard to see what was going on at that time. We have been lucky and we have found some specimens that are well preserved that give us a good idea, as well as some rocks that actually give us biochemical signatures that tell us what kind of animals had to have been living in that environment. The problem is that the bodies of those animals are very rarely found. Okay, so the Precambrian is an important period of time because it means basically during that period of time, there's almost no fossils to be found. During the Phanerozoic, which is from 542 million years ago, all the way up to the present day, that's the Phanerozoic. And the word phanero means visible, and zoic means living. So this would be the period of visible life. In other words, we can see the fossils. And this period of time could be split up, as we can see here, into 3 major groups. We're not going to worry too much about these groups in here right away, but we're going to get to some of that later on. In historical geology, this would be something of deep interest to us. But for now, we're going to split it up into these 3 groups. The Paleozoic, which means the period of ancient life. The Mesozoic, which is the period of what we call middle life. And the Cenozoic, which means recent life. And so we as human beings, we actually reside within the Cenozoic. The Mesozoic gets a special name. Not only do we refer to it as the Mesozoic, it's oftentimes referred to as the age of the dinosaurs. And you'll notice that these have these Triassic and Jurassic and Cretaceous, and those are definitely the times of the dinosaurs, especially the Cretaceous, which is where the Tyrannosaurus rex used to live. The evolution of things like fish occurred during the Ordovician and the Devonian and the Silurian. And we also see the evolution of land plants right here in the Devonian. During the Mississippian period, we see the first fern forests start to form. And so you can see that we see at this time, at the beginning part, everything is in the ocean, and by the end of it, things have already started to move up onto land, just in time for the age of the dinosaurs, and now into the Cenozoic, which also gets its own special name, the age of mammals. Okay? The only reason I put this other diagram over here was just to show you what these animals might look like if we were to draw them out properly. Here we have humans, and then we see mammals diversifying, extinction of the dinosaurs at the end of the Cretaceous. So this is something that if you have an interest in, I got this from the Britannica website. You can pause this and look through here. Fascinating stuff. For example, the Ordovician and the Devonian has just amazing plant life and animal life in the oceans. So the nature of scientific inquiry, so we're going to change it not only just from what the science is and how we can look at things, what we call paradigms for science. We're going to actually talk about what scientists do. What is the nature of our work? And so science assumes the natural world is consistent and predictable. The goal of science is to discover patterns in nature and use the knowledge to make predictions or generate understanding of a phenomena. So scientists collect facts through observation and measurements. And here we see a woman. I told you there were women geologists. Many of them, actually. I would say that nowadays there's actually more women than there are men in the field in some respects. But nonetheless, she's working on a petrographic microscope, and we will show an image of what she might be looking at under that petrographic microscope a little later on in the program. And then, of course, the most famous of which are the famous Brunton compass and the yellow field notebook, which every geologist carries. And if you were to take one of my field classes, you would be required to purchase the yellow notebook. Of course, the Brunton is way too expensive, and you would basically check that out from a school. Okay, so the nature of scientific inquiry. Again, we're still talking about this. How or why things happen are explained using a hypothesis and a theory. So what is the difference between the two? You'll hear people say, my theory is this, or my theory is that. Well, they're usually abusing the word theory when they use it in that way. The proper term is hypothesis. And a hypothesis is a tentative or untested explanation. You go into your kitchen, and you notice that somebody ate the last pickles, and you notice that there's some really well-rested, maybe a roommate or a friend that's on the couch taking a nap, and you immediately begin to suspect them of eating your pickle, and as a consequence having this comfort. It's a hypothesis. It's unproven, but that doesn't mean that you're not going to go and test that hypothesis to find out if they did it, usually by inquiring whether or not they ate your pickles. A theory is a well-tested and widely accepted view that the scientific community agrees best explains certain observable facts, all right? And of course, one of the people that we should always keep in mind when we think of theories is we got to think of this guy right here, Albert Einstein, who was kind of the quintessential celebrity scientist of the 20th century. We're going to have some new ones in the 21st century. Just give it a little bit of time. But anyways, he's got the most famous, at least the most famous hair in all of physics that I ever saw. So the scientific method is something we need to briefly bring up, and then we're going to get off of it really quickly. It's not a class about the theory of science. More is just being able to get you to understand the levels of argument and how things go back and forth, and in the end, why we believe what we believe. So the scientific method involves gathering facts. And remember, facts are the only truths that we have, right? You can go out and you can measure something. And you get, if your foot is 12 inches long, then that's a fact. That's not going to change tomorrow. That's something that we can measure, and we can write it in a book, and it will be true 150 years from now. After you were dead, your foot will still have been 12 inches long on that day. Okay, so that's a fact. Through observations and formulation of hypotheses and theory, right, there is no fixed path that scientists follow that leads to scientific knowledge. There are many different ways that we get our measurements. There are many different ways that we can interpret this information, but ultimately our goal is to get the facts and to start working from them. Okay, so in this sense, this is actually my own quote here, that knowledge begets understanding, and understanding begets wisdom. So just having that information, having knowledge, having a whole data set, which is your knowledge set, doesn't mean that you really know what is going on. Numbers and figures and drawings and pictures don't always tell the real story. Okay, to be able to do that, sometimes you need to have some understanding of some geologic principles or just some scientific principles. And then wisdom is really the articulation of this understanding to other people. All right, so we want to make sure that we not only come to an understanding of things, but we're wise in how we disseminate that information amongst society. A wise society is one that has the understanding of these facts. Earth's spheres. Now, we're going to actually go and introduce ourselves to the Earth at this point. Unfortunately, we're not going to be talking a whole lot about Earth right away in this lecture, but starting next week, we're going to be talking about plate tectonics. But let's get an idea of what the Earth is actually about. So the Earth is in and of itself actually a combination of 4 different spheres of material. There's the hydrosphere, which is where the water resides. There's the biosphere, which is where the life resides. There's the atmosphere, which is where all the air is. And of course, there's the geosphere. And you might be thinking, we're going to be talking about the geosphere the entire class, the Earth's interior, the rocks, and the soil, and that's about it. No, we're going to be talking about all 4 of them. Largely about the geosphere and the hydrosphere, but with definite inputs from the atmosphere and the biosphere as well. So don't think that we're just going to be talking about rocks and minerals and crystals, and that's all we're ever going to talk about, solid state chemistry or whatever. We're going to be talking about some really fascinating interactions between humans and our environment and our waters and our atmosphere with the rocks from which all of these things sprung. So here's a nice photograph showing the intersection of three spheres, the atmosphere, the hydrosphere, and the geosphere. And of course, you could actually very easily put in biosphere as well, because there'd be phytoplankton and regular plankton, actually, just zooplankton in the water as well. And there's undoubtedly, there's fish in here and things like this. So we actually see all four spheres together at this location. And the combination of them produces these beautiful coastlines. I don't know the exact location of this. I believe this was an image I got from your textbook. But nonetheless, you can see an amazing array of surface features, not only in the water, but in the air, as we can see these wisps of vapor coming off of the crashing waves, and of course the hydrosphere. Another way to kind of look at the Earth is to look at it from a distance, right? So let's get our first view of the Earth. Here we see a big planet. And this planet, again, we see immediately these four spheres. Now, we can't actually see the biosphere from here, but we can very rapidly surmise that in the green, or I'm sorry, in the blue, here is the ocean, and the ocean's going to have life in it. So the blue is really both the hydrosphere and the biosphere at the same time. But this area right down here is brown. This is a continent. So this is part of the geosphere. And these white swirls all over the surface of the Earth, of course, those are clouds, which are part of the atmosphere. So this is a classic image that was taken in December of 1968 by the Apollo 8 astronauts. So they had orbited around the moon. They lost sight of the Earth, and as they came back around the other side, they took a photograph of the Earth. There's a lot of really interesting symbolism that is in this picture. Not going to get into it, but this photo is called Earthrise, and it is one of the most famous photographs of the Earth ever taken. So we need to keep in mind, as we're going through this, that Earth is a dynamic planet with many interacting parts or spheres. So we've talked about the spheres. Let's get into the parts. So the parts of the Earth system are linked. It is characterized by processes that vary on spatial scales. That means, spatial means in terms of distance, how far things are away from each other. So in terms of spatial scales, from fractions of a millimeter to thousands of kilometers. Okay, so here we can actually see an image of the Earth. This is actually done on a computer program to bring it all out. These are the, right here, this is Morocco. Libya, Benghazi would be up over here to the right just off the screen. And of course, right here is Spain, France. This is the Alps. Right here is Italy, Corsica, Great Britain, Ireland, and then up here is Sweden, Norway, basically the Scandinavian countries. We're talking about thousands of kilometers of distance. Remember, a kilometer, and we haven't brought this up yet, we'll be talking a lot in metric. So a kilometer is equal to 0.6 miles, 0.6 miles. Or you can think of it this way, 1 mile is equal to 1.6 kilometers. All right, so if you're able to keep that in your mind, it'll kind of give you an idea of what it is if you're only used to thinking in miles. All right, but in contrast with the huge size of Europe that we see here, and of course North Africa, and we can see the dune fields over here, we have this photomicrograph. Remember the girl on the petrographic microscope? She might have been looking at an image just like this one, looking at these crystals that are radiating out from these nucleation points. Here's another one radiating out. Here's another one radiating out. Another one radiating out. These would be existing on the millimeter scale, and they're beautiful. Just as the giant mountains are beautiful, the small crystals are also absolutely beautiful to behold. So if you can imagine a life spent looking at these beautiful prisms and interpreting what that means in geologic systems, I think that you'd be very happy as a geologist. But the reason why I have them here together is here we got thousands of kilometers, but all of it is made up of little crystals just like this. So you can't really understand one without understanding the other. The Earth system is powered by the sun, which is to say the surface stuff, which drives external processes in the atmosphere, in the hydrosphere, at Earth's surface, right? So in the atmosphere, the sun controls the weather. The sun also controls the hydrosphere, which is to say it controls ocean currents and the distribution of rain. At Earth's surface, basically we get our warmth from it, otherwise we'd freeze to death. Right? So this is where our surface energy system comes from. A lot of people think that much of the energy that we feel coming into our atmosphere comes from the Earth itself. Actually, very little of it does, right? Almost all the energy we get is from a solar source. And of course, here's the sun coming up over the edge of the Earth, and here's the edge of the shadow of the Earth right here. It's a really kind of a neat image. But that doesn't mean the Earth doesn't have its own energy. So the Earth system is also powered from Earth's interior, which is to say heat remaining from Earth's formation, and heat that is continuously generated by radioactive decay powers the internal processes that produce volcanoes, earthquakes, and mountains. And to demonstrate this, I have two pictures right here on the top. These are both from Yellowstone National Park. Here we see a geyser, beautiful rainbow, of course, coming off of it. But this geyser is basically fueled by heat interacting with surface water and basically forming these steam blowholes that push the water out every once in a while. Almost predictably, actually, in some cases, such as Old Faithful, which is a famous geyser in Yellowstone. Next to it, actually, is a hot spring, and in that hot spring we see beautiful colors. You might be saying to yourself, what do the colors mean? Well, the colors are actually the biosphere interacting with this hot spring. There are 3 communities of algae that are actually living inside of this very hot water. Human beings would not be able to get in this water without being scalded terribly. But these 3 communities are this blue community that lives in the middle, which can survive in very hot water. We call these thermophiles. And they need the Earth system to be able to survive. But outside of this, right along this yellow edge, is a group that can't live in the blue, but as the water spills over, it cools off, but it can't actually live out over here either. It's too cold. So this is that Goldilocks situation, right? Here it's too hot, here it's too cold, but right along the beach edge right there of this pool, it's just right. And so you have a yellow community that resides there. And then as it spills over, it cools off, and a group of red algae will grow on the outside of this. So here you can see the Earth and the water and the atmosphere and the biosphere all in one interacting, where the pool of water itself is actually controlling the evolution of the algae that reside within that pool. Absolutely fascinating. So if you ever get the chance to go to Yellowstone, make sure that you visit both of these. And of course, you can't go through a discussion of talking about Earth's interior heat without talking about lava flowing out of something such as Kilauea, and that's actually where this image is from as well. You can see the lava coming down. This would be a nice ropey pahoehoe flow. We'll be talking about basalt or lava textures here very shortly. So what about the early evolution of the Earth? Well, you can't talk about the evolution of Earth without talking about the origins of the universe in which the Earth resides. So the Earth, as we described earlier, is 4.6 billion years old. But the universe itself is actually far older than that, about 9 billion years older than that, as a matter of fact. So at about 13.7 billion years ago, and of course you'll have to take a physics class to know how we know that age, but nonetheless we know it pretty accurately. About 13.7 billion years ago, something that we call the Big Bang occurred. And they've been able to, in the last 10 to 15 years, get a handle on not only the fact that the Big Bang did occur, but even on what the Big Bang looked like. And this is actually a map of radio signals that were emitted from the Big Bang that still reside in the universe, and we're able to map them using satellites. And so this very early, almost early picture, this early sonogram is kind of the closest approximation that I can come to describing this, of the Big Bang at about 400,000 years after it happened. Looks just like this. And in areas where you see the blue, that's where there's very little material being thrown out into the universe. Whereas in these red or yellow areas, there's a lot of material being spun out. And again, we could do an entire class just on the origins of the Big Bang and what we know about it. And there's fabulous classes on it. I teach a physics class also, and we talk about this very phenomenon. Anyway, interesting stuff. And if you're interested in reading up on this, you can always go to read Wikipedia articles on the Big Bang map, as this is sometimes called. So from that, you would see gases distributed all throughout this rapidly expanding universe. And in this universe, these you'd get little gas balls. And these gas balls, which of course by our scale are massive, but on a universe scale are quite small, are called nebulas. So we generally subscribe to the nebular theory of the formation of the Earth. So the Earth and the other planets formed at essentially the same time out of the same material as the Sun. And at exactly the same time is a really important thing to observe on this, right? Every single rock that we find in the asteroid belt, rocks that we find distributed on the moon are about the same age. And the oldest rocks we find on Earth go up to that point of that old age of the origin of the Earth, or the origin of the solar system. So we start finding a convergence of 4.6 billion years old, not just on the Earth, but on the moon and on the asteroids, as well as other features about the solar system and some of our neighboring stars that indicate that the Sun formed about the same time, 4.6 billion years ago. So the nebular theory proposes that the bodies of our solar system evolved from an enormous rotating cloud called the solar nebula. So here we actually see the nebula, and as things pull in, almost kind of like somebody swinging on a tire swing that's all wound up. That as you pull things in, it starts to spin faster and faster, and you start getting these material belts around this rapidly spinning gas cloud, and eventually that will form the planets. This is a subject of a planetary astronomy class that is also taught at Hawaii. So the nebular theory tells us that the solar nebula consisted of hydrogen and helium. These are the two simplest and smallest atoms on the periodic table, in addition to microscopic dust grains. This would have been composed of silica and iron, things like this. A disturbance caused the solar nebula to slowly contract and rotate. The solar nebula assumed a flat disk shape with the protosun at the center. Inner planets began to form from metallic and rocky substances, and large outer planets began forming from fragments of ices, and that's what's going to provide your water, your carbon dioxide, methane, other things to the Earth that would come later on. And just for fun, I thought I would go ahead and show this image down here as well. This is an image from Mars, actually, and one of the Mars landers looked up and tried to find the Earth, and they did. The Earth is this little spot right here, and hopefully on the YouTube video it will come through. But it's basically a speck, and that's where we live, on this little dot. So just as the solar system developed an internal structure, the Earth itself also developed an internal structure based upon the diversification of chemical properties and physical properties. And we wind up with a layered Earth with three principal layers, right? There's actually four. We'll talk about the fourth one, which is inside the core. But basically there's the crust, and there's the mantle, and there's the core. And we can see that basically the core is this big metal thing right here in the middle. It's actually made out of metal, iron and nickel. A little bit of oxygen and some other stuff in there as well, but basically iron and nickel. And then on top of that, or I should say away from that, towards the outside, is another layer, this big red unit, that's actually called the mantle. And usually the mantle is drawn in a nice red color because people think of it as being on fire or molten. It is neither on fire, and it is not molten, and it is not red. In fact, the mantle of the Earth is most likely a combination of black and green in color in terms of the rocks that are down there. And of course on the outside part is this rocky crust, which is fairly low density all the way out here on the edge. So how did this come to be? Well, the metals would have sank to the center. Why? Because they're the densest, they're the heaviest. And that molten rock rose to produce a primitive crust. Silica and silicon dioxide, which is the basis of quartz, which is a very common mineral on the Earth's surface, as well as even in basalts. Silicon dioxide is very common. Is much, much less dense than iron and nickel is. So any iron and nickel would have fallen towards the middle of the Earth, and anything lighter than that would have gone out to the outside. So chemical segregation established the three basic divisions of Earth's interior. Remember, core, mantle, crust. A primitive atmosphere evolved from volcanic gases, right? If there is any gases that were in the Earth, they want to get out. They do not want to be inside the Earth if they can get out. And the earliest primitive crust was lost to erosion and geologic processes. So What we actually now see as the Earth now is not what we would have found 4 billion years ago. Some of it would have been present. The parts of Western Australia, Mozambique, which is in southeastern Africa, and a few other small places around the Earth, and we're not going to get into details on them, would have existed back then. But everything else, such as North America, much of Mexico, most of South America, Eastern Australia, much of Asia, has really only been around for about 2 billion years or less. So for much of Earth's history, the continents have been growing and growing from these small little pieces. I hope you enjoyed this little lecture on the early evolution of Earth. We have some really great lectures still to come, and I hope that you wind up really enjoying this class. And with that, I would like to wish you happy studies, and we will see you at the next video. Bye.